Hmm. Recording in progress.
So hello and welcome to our series of executive luncheons. Today we have Dr. Luuk van Dijk, co-founder and CEO of Dedalian. They develop certifiable flight control systems for the autonomous electric light personal transport aircraft of the near future. That's how it's written on their website. Welcome, Luuk. Great to have you here, and thanks a lot for joining.
My pleasure. Thanks for having me.
Sure. So we have about 10-minute presentation from you, and then we do a short Q&A. Maybe one question up front. You guys had a report published by the FAA, which is the very famous Federal Aviation Association in the US. I guess still the #1 association.
Well, it's an agency actually. So
an agency.
It's the regulator that gives you the stamp of approvals, and no aircraft flies in the US without FAA airworthiness.
Yeah, and you had this report published. It was very exciting and a big deal for you guys. I think you will present this also later on, but just
I'll mention it. I'll mention it later on. So we had in 2018 and 19, we did 2 projects with EASA, that's the European version of the regulator, on how to argue if an AI component is safe enough for use in an aircraft. Mm-hmm. And then the FAA approached us and they wanted to know more about this topic too, and they had some interest. So with them, we worked through the specific case of our visual landing guidance system, which is a system that uses nothing but camera inputs to find a runway and guide the aircraft towards it. And so that was a 1-year project, including a flight test campaign. It was finished already last September, but then it goes through an editing process at the FAA. So it came out only 2 or 3 weeks ago. So we're very happy. It's the third big chunk of theory and practice on how to certify AI in the cockpit, which happens to be the thing we are about.
Yeah, cool. So the stage is all yours. I can get started. Thanks.
Yeah, thanks. Thanks for the introduction, Ralph. Let me see how I switch. So we are Dedalian. We're based in Zurich. We are by now 70 people since we started 6 years ago with a much smaller crew. So we bring together people from the academic world, people who know about computer vision and modern AI and robotics, with the people that know how to make equipment for aircraft, which is a massive cultural divide. So I figured when I started that there should be value in bridging that gap. We also have a data annotation office in Riga, in Latvia, where we annotate massive amounts of data which you need for training the machine learning. So the idea behind the company is that there are many people trying to start self-driving companies in 2015, 2016. And I noticed that there were a couple of people trying to build, so-called electric flying cars. And I thought, they are going to have to be autonomous too, to make any sense, because there aren't enough pilots. The pilots that are there aren't good enough to do this at high volume and high speed and high density of operations. And then these people are going to have to fly in the airspace the way it's been constructed over the last century and a bit more, completely centered around the human. So you have to have robots flying between people, like people, because these rules of how you're allowed to fly are set in stone. So we took the commercial pilot license skill test, which is a little booklet published by the FAA. My co-founder, Anna, is a helicopter pilot. She went through this and deconstructed what it is that the human pilot actually does. And we thought, okay, we're going to have to build systems that can do this only better, measurably better on every scale than the human. And for that, you're going to have to use AI, because some of the things that people do, you can currently only solve with so-called machine learning techniques. AI is a bit of a marketing term. I try to stay away from it, but it's inevitable that things are called AI this and AI that. So we now say AI in the cockpit. It's really machine learning. So how do you apply machine learning components in the cockpit? And for example, if you take these eVTOLs that people want to build for urban air mobility, they're going to have to take off and avoid cranes and not fly into buildings. And if something goes wrong, they have to find a safe place to emergency land. And they have to avoid each other in flight. And these are things that, you think that instruments help you on board of an aircraft, but aircraft are very manual affairs. And for many of these things, the pilot having eyes is the fundamental mode of operation. And some of these rules are set in stone in international treaties. So what we built was our first suite of functions in a product called the VXP. And it does the visual things that a human does with two functioning eyes and the visual cortex, namely seeing where you are, which you're required to do even if your GPS doesn't work. The GPS is often not reliable enough to do this to airworthy standards. To see where other people are flying, there's actually, as I said, these rules of the air actually prescribe that you have to look out the window and that something doesn't show up on your radar or your ADS-B or your air traffic controller hasn't told you about it. That's no valid reason to fly into them. And visual landing guidance is arguably the most important part of getting down on the ground again safe. And people do this routinely on thousands of airports in the world that doesn't have instrument landing infrastructure. Most aircraft don't have instrument landing guidance infrastructure, and instrument landing is often a two-pilot operation. So you have to have two pilots looking at if the instrument landing is doing its thing, and otherwise they have to manually take over. So that told us that the things you have in the aircraft, the instruments you have there, you can almost omit all of them, and then a human with eyes can still legally and safely fly an aircraft from A to B. So none of these instruments are vital, and there are no instruments do what the pilot does, namely look out the window and assess where's the runway, where are other people, and what is the safe thing to do. So we're trying to build this new generation of components. And then I have a bunch of slides that go into very great detail on how this works, because this is the longer deck that I forgot to swap out for the slightly shorter deck to keep this under 10 minutes. So I just skipped these two slides with the great detail. So the crucial bit is that we have this machine learned component in the middle, this AI thing. And when we started, it was very much the case that everybody thought AI, you can never get that certified because nobody knows how it works, and it's non-deterministic, and know what it does and how it does it, and that's all in great stark contrast with what the FAA and EASA want you to prove about your system. And we thought that was part misconception and part not having tried hard enough. So this neural network that's in the middle of our system that sees, oh, in this picture there's an aircraft here, or this is where the runway is. We went to EASA, the European Aerospace Safety Association agency that hands out permission to fly the aircraft or even put a computer in an aircraft. And we approached them with the plan of how to argue and how to think about proving the safety. And they were very engaging, and they got very deep into the matter. And now they have about 70 experts working on that. We have been invited to give them trainings. We did 2 projects with them to lay out this theory. And as a follow-up on that, we did this 3rd project with the FAA, because it's very important to us that the whole industry gets away from this idea that this is fundamentally impossible and can't be done. So these EASA reports came up with a process called the W. That was an invention of the EASA as a mnemonic of the steps you have to take. And the crux of the biscuit is that in traditional systems, you have this requirements management where you write down very specifically what it's supposed to do and what it's not supposed to do, because it might be dangerous. And then you build and design your system, and then you check that the design and the build actually match these requirements, and then we're all good. But with machine learning, of course, you have one computer program fiddling thousands or millions of knobs on another computer program called a model, and it uses data, large amounts of data, to verify example data that says, if this is the picture, and this is the runway, this is the picture, and this is the runway. And we have hundreds of thousands of these pictures. And now the big computer program finds the best version of the small computer program, and that's your machine learning thing. So that means that to argue or to find out if it's safe, you don't myopically look at that last program that you come up with. You have to look at the data that you use to construct this, and you have to see if that was the right data, if it's representative of reality, and if the performance guarantees that you find in the lab will hold when you go fly it in the wild. So how to deal with that? We've by now written about 500 pages of them that we generously donated to the public. Actually, in the case of the FAA, it's the American taxpayer paid for it, so it's public. With EASA, we own the reports, but we asked them to please publish most of it. We kept some secret sauce. So that's where we are. So today, and I also missed the slide where we are today. So we are in the middle of our first certification project that takes the detect and avoid system and brings it to market. So we hope to have this box in our hand with partner Everdine, an established avionics maker. They're building us the cameras in the box. We put in all the software. We do the certification with the regulator together, and that is where we are.
All right, sounds all great. Thanks, Luuk.
I don't know which slides shall I keep up.
This one is fantastic. Yeah, just let's talk about yourself to start with. When we met the first time many years ago, I think you told me that you were one of the first Google employees in Zurich.
That's right.
Is that right? That's how you came here and became Swiss, so to speak, at least live here.
So as any Swiss person can tell a mile away from my accent in German, I'm Dutch. I studied in Amsterdam and Groningen. I'm actually a physicist. I bluffed my way through a career in programming computers. And then around 2005, Google opened an office here in Zurich. And it was in the newspaper that Google was opening an engineering office in Europe. So I said to my wife, would you like to move to Switzerland? Because it seems that they're hiring. And it looked like a fun company to work for. It was, it was not a done deal that working for Google was an awesome thing back in 2005. So I came here with my two daughters, my wife, and the first dog. The one you see here in the picture is the third one since then. And I was the 24th in the Google Zurich office.
Okay.
And that was a fun time. I stayed there for about 7 years. And then I had the opportunity to move to Los Angeles and work for SpaceX on the flight controls for the rockets. Which, as you can guess, rockets have to fly autonomously because there's not much point of a monkey holding a joystick to try to get the rocket in the right place. So that was my first contact with the requirements of aerospace and this whole requirements engineering, and that the FAA, definitely wants to check that you've triple checked everything, and that if one engine dies or one flight computer dies, the whole rocket doesn't explode. So that was the second piece in my background that led to this. And then I came back in 2014 thinking, okay, what are we going to do now? And then everybody was doing these self-driving car startups. But I thought if you want to compete with Google in Zurich as an employer, you better come up with something that's really interesting. And so this idea was born out of that.
Yeah. So unpack the name, Dedalian. I'm not into Greek mythology, but I know it's based on that. So just for the
so Daedalus was the guy that was locked up by the king, surrounded by this labyrinth with the Minotaur that he constructed himself. And to escape together with his son, he came up with the idea to put feathers with wax on your arm. So he and his son Icarus flew out of the tower, and he had told his son many times not to fly too close to the sun, but he did anyway, because you know what teenagers are like. So Icarus died in the sea, which is currently named after him. And Daedalus gets lots of the blame for that. So people say, why do you call your company after this first disaster? But the underlying story is really that he invented human-controlled flight. And he was later given wings by the goddess Athena for his services to mankind. And in the Renaissance, he came to be, the prototypical craftful inventor. Although nowadays it also means overly complex, but that's a bit of an inside joke.
But he of course warned his son. Therefore, there's a good link.
You know how it is with teenagers. I mean, so it's very. got a bad rap over it. But and the other thing actually, on a more serious note, is that you have to think about the consequences of your invention. Which is also, so we try to stay away from military applications, which are abundant and which are much, I mean, it's easier to get to. So because in military applications, it's that's often misconstrued, but the certification barrier for civil applications are much higher than for military. So in military applications, as long as you roughly kill the right people, the governments will pay for it, unfortunately. And it only has to work once in front of the procurement office. But for civil aviation, there's this continuous scrutiny by the FAA and the EASA that you've done the right thing, and that's so it's a harder job.
So at the Delian, what are you guys currently really working on? What's your biggest challenge not to crack at this moment?
So we're trying to so the prototypes and the theory that was all developed over the first couple of years. We're now, since last year, we're 100% concentrated on getting this first product to market, fully certified, so that people can actually give us money and then we can give them a box, and which is at some point required for the business, that people can actually pay us for a product. So there's a lot of dots to be put on I's and crosses to be put on T's. We had, while we were waiting for the full production ready box system, we had this thing called the eval kit. You see these giant Peli cases in the picture. So we give those out to prospective customers so that they can already start experimenting and evaluating our product. So that's ongoing. With a couple of weeks ago, it was in the news that we did the campaign with Embraer in Rio de Janeiro, and so they flew our kit around and saw that it saw things that it was supposed to see. But getting the production version out is top priority for everyone.
I see. Okay. So using AI or machine learning, as I said correctly, is this now an application? I mean, your application you're looking for, is it more complicated? I would assume. And if so, can you let us know why exactly? I guess it must be explainable. You already touched on that. Is that one thing, or is it more than that?
More complicated than what?
Yeah, I mean, other applications out there. I mean,
so driving is an
industrial processes is also of course mission critical, but is it even more so?
Right. So the big difference with self-driving, for example, is so driving is insanely complex, as in it's not solved at all. Because you have to understand the difference between a rock and a bicycle and a pedestrian and a traffic sign, and you have to understand all this context to try to predict what everybody's going to do so that you don't drive into them, and then you have very limited options to fix the trajectory. So in aerospace, the robotics problem is much simpler. Anything you can see, do not fly towards. So we have to understand where's the runway, because that's the only safe place to fly towards, and everything that flies in the sky, we have to recognize it's an airplane. So that's manageable. And truth be told, you get 10 talented PhD students or postdocs, they can probably make a system that demonstrates that's a good demo. Then the big difference with driving is that with driving, you can gently apply the brakes and come to a standstill if you don't know what to do anymore. But with flying, it's called landing, and that's already the hardest part of the whole flying thing. So you can't have the computer say, I don't know anymore, let me go and land, because if you could do that, you didn't have a problem. And if you make a mistake in an aerospace incident, typically everybody dies. So they've solved this with these regulatory barriers so that you can't put arbitrary crap in airplanes, but it's a very high barrier. So we're in a different corner of the design space where the problem per se is simpler, but the guarantees have to be much stronger. So what we had to build, building the thing that it works is one thing, but then proving that it works and developing the theory to prove that it works and that theory is valid, and getting the regulator to the point where they were there. That was at least 2/3 of the problem. And so that makes it a bit different. The computer vision, the problem itself is actually really simple. We have a picture. Where's the runway? That sounds simple enough. but it's it's big enough that you can spend 60 man years on it, before you know. But so in itself, the hard part is the proof of the safety.
Yeah, you said autonomous vehicles is very, very difficult and hasn't been obviously cracked yet. And I was in San Francisco a couple of weeks ago, and I was reading that there are services out there in operation. So I was looking around, I couldn't find any. So is Elon Musk overselling this? Just maybe in 2 minutes, the core topic. What's your opinion on that?
He has, so Elon definitely has the habit of being optimistic on timelines, but he does get there, usually, eventually. So, so with the rockets, many of the launches were late, but and the landing happened 4 years after it was going to, or maybe a first version was even more ambitious. But in the end, they do land. And so the European Space Agency was standing around saying, "Oh, he's going to make the rockets land." Sure. And then 10 years later, while they were doing nothing, he had a landable rocket. And now the Ariane 5 and 6 are completely useless. And so you have to be a bit careful with betting against him. That said, the whole driving point. So Elon was not the first to put his shovel into the ground of self-driving. It's a whole industry around it. It actually started at Stanford with the guy who came to Google, Sebastian Thrun, who is currently working on Kitty Hawk, which is an autonomous urban air mobility eVTOL thing.
Yeah, oh, that's a nice transition. Yeah, so eVTOL, you just said what it means. Is this
eVTOL? Yeah, electric vertical takeoff and landing.
Right. Is this your main market you're gaining, or you are aiming for, or not really?
No, not anymore.
Not anymore. Okay.
So it was the motivating case, and it was the motivating case mainly because, again, compared to driving, there's 80 million new cars every year, and the total number of aircraft that get built in the whole world every year is 3,500. Anything big enough with the tail number. So that in itself is not enough market, I thought at the time, to spend, to get self-flying built. But then these eVTOLs came, and a volocopter is a much simpler thing than a Tesla. And in 2017, one of these first years that we were working, Tesla sold 50,000 cars for the first time. Well, that must have been 2016. So if Volocopter starts building 50,000 volocopters, then that completely changes by 2 orders of magnitude the whole production landscape. And we're getting to volumes where it might make sense to invest in this autonomy. And what is more, so a volocopter has 2 seats. So if one of them is a 50-year-old pilot who weighs 100 kilos and it costs $160,000 to train, and wants to be paid on the order of $75,000 a year, and that would be cheap. Then making this autonomous is a big step. And then so you can come a long way with automation. So you try to eliminate all the uncertainty from the operations up front. You fly restricted trajectories. You put down rules that no drones are allowed there, and only people who have the transponders and you fly. Instrument flight rules, and so you can come a long way with binding this down. But what people have been trying to do in other parts of the airspace, you find you have a safety pilot, and the safety pilot apparently does things that your automation doesn't do. So if you analyze that, the role of the pilot is not to control this stick or to push these buttons, because that can be automated. The role of the pilot is to maintain automation. To maintain safety. Safety is a dynamic control problem. And with that, we took a fresh look at the whole aerospace industry. And then it turns that retrofit market is actually quite big. So there's, for these 3,500 that get produced every year, they do have a lifetime of 20 or 30 years. We just bought our own aircraft in Switzerland, which was built in 1979. And this problem that human pilots is responsible for maintaining the safety, that's still a very interesting problem that we're cracking with the machine. So we're trying to build a machine that can do that, because to move the stick around, you can go by a fixed hawk, which is this amateur flight control thing that you can put on your toy drone, and that's all great. But that's not airworthy, and it does not actually solve the problem of maintaining safety.
Right. Yeah.
So with that, we have a new. Oh, sorry. So we have already a couple of years ago we realized that our market was not the eVTOLs, because they're also, they're talk about disappointment. When we started 6 years ago, we thought that by now they would be flying and in operations, and we knew that they were going to be manned operations first. But by now we would have seen operations. So that's like with the self-driving, it's taking a bit longer than everybody.
Right. So related to safety is security, of course, right? Maybe you can spend a little, give us some insights on what you guys are doing to make sure that not suddenly the bad guys take over the autonomous flying.
I think that's in general, the world is super naive on the risks there. So people want to have the Internet of Things, and then wouldn't it be great if your aircraft was also a thing of the Internet? I think it's a terrible idea. And actually, if you go back to the rules of the air, the ICAO, International Rules of the Air, I think it's Chapter 2 says that your decision capability, the pilot has to be on board. Or the way I read it, all the knowledge and the control systems to make decisions have to be on board, because you cannot rely on a round trip over a command and control link for anything with the most trivial commands. So you have to have your system on board. So our flight control system is on board, and it's designed. Autonomous means by itself. So it is given a mission, and then it executes this mission while maintaining safety. And that should not, be a thing of the Internet. So we're not going to run our algorithms to control the aircraft in the cloud and have some communication thing. But the attack factor is the attack surface is actually a lot broader. So you have to make sure that the bad guys don't go in while you're doing your machine learning training, and you have to very accurately trace what happens to your code, and so that the cybersecurity of the software engineering is something you have to build in now, because after you've written a million lines of code, it's going to be very hard to prove that nobody messed with it. So there's actually a thing I learned at Google, how to do software code management, and how to do the reviews, and how to do the development process, so that at the end you can sort of trust what you do. And then when I went to SpaceX, that was actually a notch higher, the rigor with which it was done, and that also helps with the safety and security impact. So the system we're building should, you cannot log into it from the outside while you fly, and I think that's an important distinction to hold.
And to maintain the communication navigation infrastructure, I mean, you theoretically you could do some jamming or something.
Yes.
So you must have some protection against it. But that's probably a general problem for all the aircraft.
Yes, right? But that's actually, so that's the reason why you have currently a live pilot with two eyes on board who says, I don't trust this GPS because I look out the window and I still see this coastline. So our visual positioning system actually does exactly the same thing. It will tell you that the GPS cannot be trusted because we know where we are by looking out the window. And so if your GPS is there and it's reliable, you should totally use it. But a system that can only fly on GPS, that's how Iran got the drones from the United States, by spoofing it and making it think it was back home, which is, no human would make that mistake. It's the same with, in the end, as a human, you trust your eyes because it's very rich information. So it's going to be very hard to project an image on our camera while we fly that will mess with our state estimates. That's also why people get really upset if you shine a laser at an aircraft. I mean, the police will come and look for you. And so that's actually, you can call it cybersecurity if you want. It's a very lower level of sophistication in the attack.
Yeah, talking about the people. So the public adoption of this, is this also a big challenge to overcome? And I mean, you have do you have to address this as a startup? You just go with the flow.
Well,
people might not like it if there's, I mean, just about the idea there's something autonomously flying up there. What if it crashes on my house or not?
Yes.
Right. Same with autonomous vehicle, but okay, we're not. But
so people often say, it's the same with privacy and these things. People say that other people will be upset about this, but then, people are shown the price of the ticket. They get into the 737 Max, the next day.
Right.
I don't think anyone did not take a flight because it was a 737 800 Max the day after they were being put in service. And so more generally, it's the job. So the reason we have an FAA and an EASA is because the flying was a Wild West around the 1950s. And so these government agencies were given the task on behalf of the public, make sure that it was done responsibly. And the reason we have to meet these incredibly high bars to put our systems in an aircraft is exactly for that reason. So I think passing the regulator's bar it's good that the regulator on behalf of the public maintains this bar, because the public would just get into anything if it was cheap enough. So the public has to be protected against themselves. So I'm more cynical than cautious about the public acceptance once these things are there. And then what was your other point? I forgot my train of thought there. So 100 years ago, an elevator had a guy, pushing the buttons, nice uniform, and then the elevators were dangerous at the time. And then rules were put in place, and the elevators got safer, and you could actually just push the buttons yourself. And now, if you go into an elevator and there's a guy standing there to push the buttons, you think, must be some sort of maintenance. There's something wrong with this elevator. So I think we will get to the point where, for flying at least, this will be a similar transition. And yeah.
So there are regulations in every different country on top of these FAA and EASA, right? Where do you expect this to be used commercially first? Is there any country up to do this, or pretty much everywhere?
EASA land is pretty homogeneous in this respect. So Switzerland voluntarily submits itself to the regulations of EASA. And America is a big place. So in America, you have a big tradition of it's called experimental aircraft, which are not allowed to use for commercial operations, but it really makes flying much more democratized, and it makes it much easier to experiment. That's what experimental is called. So I think also the most promising contenders for the eVTOL market are currently in the United States. And so they're probably close to market. So that's probably what's going to happen first. So New Zealand has even more flexible rules, but it's not so much, there's not a lot to do in New Zealand, or you can
fly around. Beautiful landscape to fly over.
Yeah, it's beautiful landscape, but you don't have to fly there. You want to walk there. So I think United States and probably the Bay Area. So some of these problems are clearly. So some of the ways the problems are addressed are clearly by billionaires who think that one of humanity's largest problems is being stuck in a traffic jam, where in reality that's only a problem in San Francisco. I mean that you're a billionaire and you're in a traffic jam. Yeah, but there's slightly fewer billionaires. With that bias, that's probably they're going to fly over the bay, and everybody has a good time. Yeah. I'm also less optimistic on what a big change the eVTOLs will make, but I do think so. I think it's not going to take away 10% of the road traffic, or 2. It's not even going to take 2% of road traffic away. Right. But flying in general, there's clear demand to do more flying. And there is a pilot shortage, and you can currently. So this has been the way we look at it, you have safety, you have the price of the operations, and you have the density of the operations that you can do in a certain volume of airspace. And currently, you can only improve one at the cost of the two others. So if you want to move that whole front forward, you have to come up with new systems that take over this uniquely human task of doing the safety maintenance. And that's what we're trying.
All right. Maybe last question on the Delian itself, startup still. Nice round of funding, just beginning of the year you published. So what is your big vision? Where is this all going towards?
So the funding round is supposed to get us to markets and financially independence in the next 3-4 years. Okay. It was designed with those parameters in mind. I think the regulator has clearly told us, don't come to us with ambitious and autonomous things until you first can show that you're a good co-pilot. So I think in the next 5 years, we're going to roll out this co-pilot, and we're going to gather the data to show that things are better if the pilot doesn't touch anything. And then as we gather that data and the evidence, then in 10 years from now, it will be normal that the human doesn't do anything, and we can start the argument that they might as well not be on board, at least not to do this flying. Because I see no reason why the machine couldn't be better at this job now that we've actually finally started tackling it. Yeah. And I don't think so. I think with some realism, I'm not going to promise autonomous flying things tomorrow, because we're 6 years in, and we've just managed to define how to even prove that. But give it another 5 to 10 years, I think that's definitely going to happen.
All right. Great. Thanks, Luuk. Was super talking to you. All the best for you and your startup. I'm always very excited to see people who are innovators and risk a little something or a lot. This is what we need, even more so here in Europe and Switzerland and maybe in the US. Thanks. All right. Thanks.
My pleasure.
Bye.